All right. Just like dq, just like if I have a sphere, okay. Uh, and let's say this is the z direction, and let's say this is the y direction, and this is the x direction. Uh, Actually, first I'll say the proof that they say, and then I'll explain it. They say this is a 3D area element on three-dimensional hypersurface embedded in 4D. What is the equation that defines that hypersurface? It's just E squared equals P squared plus M squared. C is 1. Now, so if I have a 4 vector Pu, which is equal to Px, Py, Pz, and E. Okay, so the E is just the fourth element of this P, and E squared minus P squared, which is equal to P mu times P mu, is just equal to M squared, and maybe there's a minus here. So this is kind of like the dot product of a vector with itself, and it's equal to a constant. It's like a vector, so it's a four-dimensional sphere that has constant length, and we have a four-dimensional sphere. This is the three-dimensional area element that is proportional, well, that's perpendicular to the vector P mu. And I'll say 4 here to show that it's perpendicular in the four-dimensional space.
Okay.
And so this is the three-dimensional area element in a four-dimensional space, but it's the but how do you depict an area in the space? Well, with a vector that's perpendicular to the area. So this is actually dqp is actually the fourth element in the vector that's perpendicular to this area. And what vector is perpendicular to this area? Well, P mu itself. And therefore this is proportional to P4. Therefore dqp is proportional to P4, which is equal to the energy, and therefore dqp over E is a Lorentz invariant. Now, did anybody understand that? I told you, if I proved it, you would stop believing it. But let me just give you an analogy now. Suppose this is a sphere, a unit sphere. I'll draw it again. And let's take the z direction, and this will be the y direction, x direction. Okay. Now the equation for the sphere, which is a two-dimensional hypersurface embedded in 3 dimensions, is x squared plus y squared plus z squared is equal to r squared. Okay. Now this is equal to x vector dot x. And now the element dx dy, let's say we took a patch on the sphere around the z-axis, but on the sphere. Whatever it is, it's a very small number because it's a differential element, but whatever it is, I can ask how would its value transform under rotation? And you can see, well,
it shouldn't change.
No, it does, because dx dy is the projection of this onto the xy plane. Imagine it's the length, it's the area of the shadow projected. So it's really just
okay.
If I rotate it away from the z-axis by cosine theta, then this transforms as cosine theta, right? If I rotated it to the north pole to the equator, dx dy formally goes to 0 because it has 0 projection. Now z, the z component, the z coordinate also, that's just z. It also transforms like cosine theta, right?
Yeah.
Because I'm on the sphere. So dx dy over z, where again z is the third component of the vector, invariant under rotation.
Shouldn't it be dz?
No.
Z?
It could be dz also transforms as cosine theta,
Right.
but that's the dz. But there are two differentials here. You're talking about the dz that if I made a cube, it would be dz would be proportional, would be perpendicular to the hypersurface, whereas this dx and dy are parallel to the hypersurface, and that's why. And it's even more confusing for a Lorentz transformation because you can always get to a bigger momentum with a Lorentz transformation, even though the length of the 4 momentum remains constant. So in the Lorentz transformation, the change in energy can be accomplished by a Lorentz transformation, so it's the same as what you got from the symmetry operation. It's just because it's the same doesn't mean you should confuse it. Because under rotation, they're two different things. This is in the frame of the hypersurface. The area is constrained to be within the hypersurface, and the perpendicular element is the z vector, which is perpendicular to the surface. And if I rotated it over here, it would be this vector that's perpendicular to the surface, and this would be z prime. But z prime is z times cosine theta, so that's why you say z. Because if I said dz, I would have to specify that I meant the dz perpendicular rather than parallel. So the energy, in some sense, the energy is energy is equal to gamma times m, but it's equal to gamma times dE dm when p is equal to a constant. I mean, changing m is sort of like the vector that's perpendicular to dqp, and that gets even more confusing. So I'm just going to say z here because you see it's also So anyway, that just proves, all that was to prove that dQp over epsilon is a Lorentz invariant. Now there's another way to transform photon energies. It's also done in Landau and Lifshitz. It's one of the problems. And it's just, you note that the energy density, energy is the fourth entrance in the 4 vector, but energy density is the 4 element in the 2-dimensional tensor T mu nu. So I'm just going to say,
Can I open the door? It's too hot here.
open the door or turn on the air conditioner, either one. But turn the temperature to 27. Okay. Actually open the door also because I want fresh air. You can also note that U prime, which is the energy density of the photons in the electron frame, is equal to T U prime nu prime. Oops. Which is equal to no, I want these up here. No, I didn't. So, if you remember, we discussed these transformation matrices last time, and if you know how to transform a second-rank tensor, you can also get the energy density that way. And like I say, it's usually just gamma squared if it's isotropic. And there may be and 4/3 is there for other reasons. I think it's just that the average energy of the photon, if it's isotropic in one frame, then the average energy of the photon just goes up by a factor of gamma. And the density also goes up by a factor of gamma. Wait, did I say that right? Sounded right. Is it right? Yeah. That's the way I think of it. The photons, if you have a box of photons, they're isotropic in the frame of the box, and you make a Lorentz transformation. The box gets contracted in one dimension, so the density goes up by gamma, and the energy of the photons goes up by a factor of gamma. So the rate of power emission for an electron that moves through a photon bath goes as gamma squared. But there's also a beta squared in there in case beta is not quite 1. Okay, now I go to lecture. What time is it? 3:30?
No.
It's about 3:35.
Oh, 3:17. Oh, is it right?
No, 2:14.
What?
Okay.
It's 3:15?
Yeah.
Hey, did this self-correct?
Yes, can do it. Can do it.
Oh, I'm sorry.
It's from your computer.
It's from a different computer. No one is correct. Okay. All right. So now I'm going to No. How do I get that? How do I get to the next page of the lecture notes?
I think it's there only, that recorded.
What?
In that same folder, probably it's there. Lecture 2, the upper one.
We're on lecture 1, part 2, right?
Yeah, and the most upper there is lecture 2.
Yeah, but
Which one do you want?
I want lecture 1, part 2.
It's there.
This does not look promising. Where did I just write, for God's sakes?
Lecture 1.
Yeah,
You can see
the
that
lecture
on the right one. Yeah, no. Go down a bit.
just beside the lecture 1 part 2, yeah. Just save it, sir.
So lecture 1, part 2 doesn't go any farther than lecture 1, right?
So could you please save it?
Alright, I'm saving this as... I'm saving this
Lecture
as...
1 part 2. No, this is lecture 1.
Yeah, but I'm saving it as lecture 1. How am I supposed to type? Where's the fucking... No. I keep saying I'm getting an apple. Getting an apple. Where's the fucking keyboard?
You can rename anyone. I mean, lecture 1 is probably this one, so you can rename this one also.
Where's the fucking keyboard?
Maybe if you press on it.
When you
What?
tap there, it will appear.
If I what?
You could
If you
press it.
tap with the pen, then
Yes.
it should appear. There, the
Yeah,
small
there.
one.
Get it quick. Oh, look, the cursor starts. No matter where I put the cursor, it starts and disappears before I can get it. That's great.
You have to be faster.
You have to use pen
Yeah,
because
fine.
you're using pen. So don't switch between pen and this. You use pen, use pen.
Tapping, but now it knows what I'm... See, I heard you.
But now, now you're tapping anywhere on the screen. Tap there where you need to type. So you type in file name. So you tap there, it appears now.
Okay. How do I hit... Can I hit shift and then...
Yeah.
Lecture 1, day 3.
Nothing I can do. I get on the person. Let's read it again. I got another question. One in the CD and one in the
Alright, now I'm going lecture 2. And I'm closing this.
This is the part who is lecture
What?
2. This is lecture 2. Like this
Yeah, but lecture. Didn't lecture 1 have something about Bremsstrahl in it?
Yeah. Yes.
No, didn't it have something about synchrotron emission?
No.
This goes the same as the.
You sure
in the
lecture
stopper,
2
no?
starts here?
Yes.
It's not enough to say it's the same as the inverse Compton, just the energy density is going to the magnetic field.
Yeah, it is. It is, but it is nice to derive it, especially the 4/3. I'm just going to skip it for now and start talking about radio spectra.
It's there. Yeah, to the right.
Has this been going all along? Yeah, I guess so. Basically, if you have an the synchrotron radiation works the same way, and the average energy, or the average frequency of the photon that's emitted is of order gamma squared times the cyclotron frequency of the. But it's the formal cyclotron frequency. It's oh man, you know what? I'm just gonna write here. The typical frequency is equal to gamma squared EB over m sub e c. M sub e is the rest energy of the electron, and
Why the gamma squared?
well, if I derived it, you would know. And basically, it's really gamma cubed times EB over gamma m sub e c. This is the real frequency at which the electron gyrates. And basically when the electron is gyrating, it's emitting it's always accelerating. The acceleration vector is always towards the center of the gyro orbit. And the power emitted is equal to E squared A squared over C cubed.
Okay.
What are the other terms?
What?
What are the other terms? Apart from E square square.
There's two or three.
Oh yeah, there's a factor is
Yeah, just three or three.
Well, this is for non-relativistic. For relativistic, I don't exactly. If I unplugged this computer and plugged in my old computer, I would get my lecture notes in. Look, when Arca, when I asked you to put in lecture, you always put in from where I left off last time. If I say lecture 2, or lecture 17, I mean wherever we left off last time. If I said the second lecture, I meant, well, you know what I meant. Okay, alright, I think I can actually do this. This is if I go into the frame of the electron. This is unprepared. I've never done it this way before. Let's see if it works. A is equal to EB over times C. That's the acceleration. In the electron frame, so I have to put a B prime here. B prime is, let's say, gamma times B.
It's EBC squared. Because EBC is false.
No.
Divided by MC.
Okay, see.
You should not
EBC is
see the
false.
denominator.
No, this should be.
No, that's okay. It's a V cross B.
No, this is a frequency, and this is the frequency, and this is the velocity. Right?
Whereas Lorentz force m dv over dt is V cross B. So V is C here. The assuming it's a relativistic electron.
That's the force, yeah.
So V cross B, so B is there, the denominator. C is velocity and Q is E. And divided by m, so m is gamma m.
Yeah.
So that gives you dv over dt, that's acceleration.
Yeah, and what was the answer?
Oh wait, you have normalized to C, so that's okay.
It must be one
No, I didn't normalize to C.
No, that's absolutely okay.
I still think you need to do C
Uh,
squared.
No, EB over MC has units of frequency. So this has units of acceleration. I mean, granted, the C cancels.
Yes, okay.
No, this isn't going to work. B prime is equal to...
But Lorentz force is EV cross V.
What?
Lorentz force
But this is not in the
EV
frame
cross V.
electron, this is
What?
The Lorentz force is EV cross V.
Dimension.
So it's EBC.
It's one
It's
over
false.
no, that's uniform electron.
What?
No, but
Lawrence
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 Fence is not EB cross.
Okay, so
It's not E times B. I'm sure.
Times C, right.
So this B is in the
Clockwise,
lab
clockwise.
frame. There is not in the frame of electron.
B is in the frame of the lab, but the
It's okay,
electron.
it's okay.
Yeah, I'm sorry. B should be in the frame of the lab. But this formula is wrong. Look, the width of this is delta theta. It's of order 1 over gamma. That part I know. And the time in which the observer is in the beam is equal to 1 over the frequency in other words, it's the time it takes to go the full route times delta theta, which is equal to 1 over gamma, and the frequency is EB over gamma m sub b c. So delta t is mc over eb times gamma squared. No. Yeah. Okay. Yeah, delta t is the amount of time that an observer watching sees from the side sees another observer in the frame of the beam. But now, what does this observer see? We call this delta t sub r because it's the received observer. He sees the emission for much less time because the beginning of the pulse, the particle was here. At the end of the pulse, the particle's here. The particle is moving towards him at a speed of beta c, which means that the difference in time when you emit pulses, if a source is moving towards you and emits pulses, the difference between the arrival time of the
Doppler effect.
it's not the Doppler effect. It's the arrival time effect. The observer's here, and you're moving towards the observer. You emit a pulse here, and you emit a pulse here at a later time. This difference is delta r is equal to c times delta t. In other words, the amount of time that the observer was in the beam.
Okay.
But this last pulse was emitted by the time the last pulse was emitted. The source which emitted the first pulse from here is already moved to here, and this remaining distance is R1 minus R2. Is equal to beta C delta T, where beta is the motion of the source.
Let's see.
So if beta is close to 1, this was moving almost as fast as the light. So the light was here and it was here when it emitted the last bit of light. So therefore the delta T that the observer receives is equal to let's say divided by C, right? No, sorry. This is R1. I'm sorry. It had to go from R1 to here. You know what? It's just the difference between this point and this point. I don't know what to call this point. Let's call it R3, alright? So, delta T received is R2 minus R3 over C, right? That's the difference in arrival time between just a second. R3 is where the first light pulse was at the time the second light pulse was emitted.
Okay.
And it had a lead of R2 minus R3. That's the distance separating the first light pulse, and so the time separating is just the distance separating and divided by the speed of light, and this is equal to delta T times 1 minus beta, right? Because R1 minus R3 is C. R1 minus R3 is equal to C delta T. Alright, so there's a 1 minus beta here. And therefore, delta T received is equal to 1 minus beta times delta T. And this is approximately 2 gamma squared delta T. Gamma to the minus 2. So the frequency The received frequency is basically 1 over delta t times gamma squared. And delta t, we remember, was just the original un-Lorentz corrected cyclotron frequency. It was just MC over EB, right? Because the gammas canceled out. You agreed to it at the time, so so this is just gamma squared EB over MC.
So there will be a two factor
What?
factor of two that came in delta T obviously.
It's because 1 minus beta
Yeah.
is equal to
2 by gamma square.
1 over 2.
Multiplied by 2.
it's equal to 1 minus beta squared over 1 plus beta.
It's 1 over 2.
No, but this is 1 over 2 gamma squared. This gamma squared is 1 over this. So there's a 2 next to the gamma.
So in that frequency R, mu R, there
Sorry, this I should have written it that way. Okay, there we go.
So then it becomes 4, 1 over 4 gamma squared.
Yes.
No,
Yes.
no.
Yeah.
What's 1 over 4 gamma squared?
No, you
Oh, 2 by
have it in
minus
bracket
2.
with
This
parentheses.
is above minus 2 power.
1 by 2 gamma whole power
No.
square.
No. 1 plus beta is approximately 2.
No,
This
that's-
is when beta is
So
approximately
this is
1.
fine, this is fine, but in that expression within the first bracket, there is 2 gamma, 1 by 2 gamma square. Whole square.
Where? Point. Which?
1 by 2.
Right, 2 gamma squared to the power of minus 1.
No, in other words, I had it right the first time.
2 inverse 1.
No.
1/2 gamma squared. There we go.
2 inverse.
Everybody happy? It's been a rough day.
But why is it 2? I don't understand. Because 1 minus beta squared is 1 over gamma squared. But,
And it tends to 1.
huh?
Beta tends to 1. Beta tends to 1.
Oh, yeah, this is right.
Now, did I write this after? Or where's what I just wrote?
And the
Is it-
topmost part.
It's top. Okay, good. So now, we know that the frequency of synchrotron emission is of order of this, and the power. To get the power, I would just do a transformation. E is equal to E plus beta B times gamma. Is that a correct Lorentz transformation? Uh,
What do you say?
mm,
Is that like
This is the electric field, yeah.
I don't know.
And in the frame of the lab, let's say there's no electric field. So E is equal to gamma beta B. In the frame of the particle, there's zero velocity, so the Lorentz force is just E times E prime. Over M. This is what A prime is. And in that frame we can use non-relativistic formulas. So P is equal to 2/3 E squared M squared times gamma squared beta squared B squared and this oh, okay, and there's an e to the fourth here because this part is just the a prime squared, but there's another e squared out here, and there's a c cubed down here. Alright, let's see where this gets us. So this is 2/3 times e to the fourth over m squared times gamma squared beta squared b squared. Now, what can we do with this? Well, we know that sigma Thomson is equal to c cubed. We know that sigma Thomson is e squared over mcv c to the fourth times 8 pi over 3. No, is it 8 pi over 3 or is it just 8 pi?
It's 8 pi over 3
What?
Yeah, 8 pi over 3.
So I can write that the power is equal to 2/3 times sigma Thomson, and then this was c to the fourth, and I want to get back to c cubed, so it's times c times gamma squared beta squared b squared
And it's e.
over 8 pi.
Yeah, but in here it's supposed to be e to the fourth.
It is e to the fourth.
No, in here.
Oh yeah. Oh right. Now, I don't like this because I should have this should have been 8 pi over 3, and therefore I should have I don't know. I don't know where I went wrong. Oh. I know, yeah. I know why. Haha. This was assuming that the velocity, that beta squared, was perpendicular to B in this transformation. Now, if I average over an isotropic distribution, that's equal to 2/3 of the beta squared that I assumed when it was just perpendicular, because beta squared is equal to b perp squared plus b parallel squared. B perp squared is bx squared plus by squared, so it's for an isotropic electron distribution, this is 2/3 of the beta absolute, and here I meant beta absolute always. Let's back it up. Alright, you get the idea. So now I can write P is equal to let me write it this way. For an isotropic electron distribution, P with velocity let's say the electron's speed, so there's no direction, beta times c, P is equal to 2/3 times P when beta is perpendicular to B, equal 4/3 times sigma T C gamma squared beta squared times B squared over 8 pi. I just write as U as B. So it's exactly the same formula, it's just the energy density of the photons replaced by the energy density of the regular field, and you even get the 4/3 as being the same. So this tells me now the rate of synchrotron emission and the rate of inverse Compton emission. and they're the same. They're both proportional, and then just picture it as an electron that has area sigma Thomson, moving at the speed of light. It's sweeping out a certain amount per unit time, and a certain amount of volume per unit time, and 4/3 gamma squared times the amount of radiation that was originally in that volume. Just think of it as a snow cloud that's boosting everything by gamma squared. Now we can think about, we can talk spectra. Suppose I have, it's,
we have a Chantrigul.
I know, but I go until 4, the Tirgul doesn't start until 10 after 4. With who? With who? No, I'm stopping at 4. I'm stopping at 2 minutes.
Oh, okay.
Because this clock is 2 minutes fast.
Oh, okay.
The point is I can talk about an electron that has a distribution in energy. It's an energy spectrum. They have different values of gamma. They're in the same field or in the same photon bath, but they emit, each one emits at a different characteristic frequency, and that gives me a typical photon frequency. Synchrotron or inverse Compton. It'll be a power law that depends upon the electron's spectrum, but it won't be exactly the same. It'll be different, so we'll talk about that next time, which is tomorrow.
Yeah.
2 to 3?
You do push time? Exactly 2?
10 after 2.
No, I can do it exactly 2, just to be sure.
10 after 2.
Okay. Thank you very much.
Thank you.
Okay.
Little different.